Thank you, everyone, for coming along to another SGA meetup. This time we are talking about optimizing game performance strategies that scale with Torbjörn Söderman. Um, my name is Ben Abraham, and I am just going to do a really quick introduction to, whoop, if my slide deck will advance on my other screen. There we go. To the scale of PC gaming impacts that we could have with energy efficiency improvements, and just sort of set the scene a little bit on why I think this is such amazing and important work that Torbjörn's doing, and why I hope that the industry takes notice and is able to implement it themselves in other contexts. Um, yeah, and then I'll just hand over to Torbjorn himself to talk through what he's been doing, why he's been doing it, what the benefits are for players and for their game goals. And then we'll have a bunch of time at the end for open Q&A. So if you have questions, feel free to put them in the chat or hold on to them until the end, and we'll have plenty of time for that. If this is your first time coming along to one of our SGA meetups, the SGA, or the Sustainable Games Alliance, is a not-for-profit cooperative owned and operated by the games industry. Uh, Games companies own the SGA that tell us what to do, and we help them to do that. It's all about helping the games industry become the most sustainable form of entertainment they can be, with a focus on decarbonization, because we know if we don't get that right, then kind of none of the other stuff that we do really matters, right? This is the number one priority for, the next few years ahead. The approach that we take is that we are developing a self-regulation framework to measure and calculate emissions from all the parts of the games industry, the games production process, games distribution, to gameplay, which we're going to be talking about in today's meetup. And we're all about facilitating this knowledge, sharing it with our members and the wider industry, and helping by developing tools and collecting the data that you need to save time and ideally money as well. So this is our core team. I introduced myself. My name is Ben Abraham, and I'm the research and standard lead. We're also joined by Maria Wagner, who is our managing director in the call, I think, but just listening in. And I don't think you can make it today, but Jiri Kupainen is the chair of the SGA board. We're backed by industry heavyweights like David Helgeson, Petri Javaletto, and Yanni Karma, and we also have an advisory board that keeps us honest and makes sure that we're avoiding greenwashing. We have members from all across Europe primarily, but increasingly around other parts of the world as well. I think we're over 30 members now. You can see some of our members here, heavyweights like Cybo, Sports Interactive, Remedy, and a bunch of associations and indie developers as well. And we thank our members for their support. So really quickly, how big is the games market today? I just saw this chart recently from Game Discover Co., which estimated the monthly hours played on Steam, putting that figure at about 5.4 billion hours a month. That is a lot of gameplay across about 180 to 200 million users. Every single one of those gameplay hours on Steam has involved a device that uses electricity. And almost every part of the world, there is still some element of fossil fuel power generation going on. So for whatever country they're in, whatever part of the world they're in, there's a little bit of fossil fuels to a lot, depending on where they are in the world. So that means climate impacts, and that means emissions, greenhouse gases. So we've done a little bit of modeling. We've applied a model based on the Steam hardware survey, looking at the split of different hardware components across the PC player base. And my best estimate is that PC gameplay on Steam could emit as much as 10.5 million tons of CO2 per year, which is like a small country. So that's pretty significant. So what can we do about that? Well, we have some of the solutions already. We've got things like energy efficiency. Fortnite's eco mode shaved about 9% off of the average console's Xbox Series X player power consumption. And if we apply the same sorts of estimates to the PC player base, so even if we're just applying eco modes, then we could potentially save as much as 750,000 tons of CO2 per annum just by having eco modes on Steam. And that's the equivalent of 175,000 cars taken off the road, or closing two gas-fired power stations. Or we build 224 wind turbines. This is sort of the equivalent. Think about which one's sort of easier. Or we could grow 12 million trees for 10 years. And this is in the context of, we're reaching the end of the year now. We're revising the annual carbon emissions budget. And this is the most recent projections. At the start of next year, we are projected to have about 4 years left to keep under the 1.5 degree budget. That's the sort of Paris Agreement that we're trying for. That's like the best chance that we have of limiting dangerous warming. Anything above that, we start to roll the dice. We start to load those dice towards dangerous global warming. For 1.7 degrees, we have 12 and a half years, and for 2 degrees, it's 25 years. So this is like, rubber hits the road. This is the time. So reducing emissions, reducing the energy consumption of our players buys us time. It buys us time today that we can use to continue the transition to increase renewables. And under the Paris Agreement, the developed world has a responsibility to reduce faster, to leave room in this budget for other parts of the world to develop, this sort of equity principle. So the good news is, though, that we have the solutions already, right? We have the technology, we have renewables, and increasingly, we have real insight into the energy consumption of our devices and our players. So, in that context, let me hand over to Torbjörn to talk about what he's been doing with goals.
Yes, so I'll need to share that one. So you need to stop sharing. Thank you.
There you go.
Thank you. And you can see my slides, right? So yeah, this talk is called like optimizing game performance strategy at scale. I think unfortunately it might take a bit longer than 20 minutes, but I'll try my best to keep it fast. So yeah, my name is Torbjörn Söderman. I currently work as a technical director at Goals. Previously, I worked at DICE doing a lot of Battlefield games and Mirror's Edge. Also worked at King doing Crash Bandicoot on the Run, and Tokaboka making mobile games. So I have sort of a mix of console and mobile experience, you could say. And for me, like performance improvements has always been around like having a business case that you need to have in order to invest this type of money. So you need to make the necessary investments in resources and time. You also need to provide why you should do this. Why is this needed? And what I've sort of come to the conclusion over the years is like performance, playing experience, profit, and power are sort of linked. And I like to call that the sort of 4P strategy. So performance improvements improve these areas quite a lot, and this is basically how. So player experience is usually the primary use case for performance optimizations for both games and server and client side as well. Like if you want low latency, stable frame rate, it's important that your game is like good at that. It's an easy sell for the sort of decision makers to do that. And in terms of profit, like improving performance on the server side gives you obviously lower operating costs. And that's from sort of a business perspective is also really important. And it also gives you from the client side, you'll have like a larger user base because you can target lower end platforms if you do a lot of performance optimization. And this is also directly linked to power consumption. Like the less like resources you use on the server side, the less money you'll make basically, or the less power you'll take, and that sort of gives you more spend basically. And with room to spare on the client side as well, you can throttle performance. So you'll reduce the power usage and you will reduce power carbon footprint as well. So a bit about Goals and what we're doing. So Goals is a fast-paced fast-paced, competitive, free-to-play game, and it's an esport-ready football game, and it comes out on PC, Xbox Series S and Series X, and PlayStation 5, with a big focus, I would say, probably on PC right now. I'll show you a short video so you know what this is about. And this is actually a slide I took from Ben's presentation, so thank you, Ben, for this one. But this one shows sort of in terms of scale, what should we focus on as game developers? Like, what is the most bang for the buck? And I think that's sort of the key to doing things like this. So obviously, like, use of sold products is gameplay. So the more you can target actual gameplay or the client, the more you can actually gain in terms of like emissions reduction, basically. And then you have like the data centers, the category 1 part here, which is the game servers, the backend stuff that we're using. So targeting that is also great from sort of an emission point of view. And then you have like downloads and installs, like how can you sort of minimize this in any good way? And this is actually what I'm gonna focus on talking, like what have we done in each of these categories to make sure to try to be like, just be a bit better, basically. And it also impacts, obviously, like from a player experience, it also gets you a better experience as well. So let's talk first about SENTEC. And SENTEC is like a data-oriented simulation and networking engine. It's capable of running with or without Unreal. It solves the problem for games with close physical proximity and interactions with 2 or more characters. Like, neither the network model of fighting games nor the model in shooting games really fits sports games, and there's no third-party solution that solves this problem for sports in a good way. And if you look at the player experience part here, like SENTEC is server authoritative, which is like makes it esport ready. It is using client forward prediction with rollback, the same stuff that is used in fighting games, which makes it feel like a single player experience. It is very latency tolerant. We can run the game in 200 milliseconds of ping, like cross-continent gameplay, and it still works. And since the network model is built in the way it is, like replays of the network is easy to do because you're basically just replaying the network stream. And it's processing data in a very efficient way since it's written in a data-oriented way instead of an object-oriented way. So it's like performance is the key here. And from cost efficiency, like we can now run multiple game servers per CPU core. So basically stack a lot of game servers per CPU cores. We have minimal data transfers from the server to the client, and we're saving significantly on the CPU hosting cost due to this. And we also have like benefits on the game client due to the efficiency of the SENTEC technology. We can run on really low spec hardware, and that obviously opens up for a wider market share. Rome wasn't built in a day, and obviously SENTEC wasn't built in a day either. So like back in the day, we prototyped this on the Unreal stock network model, which is sort of used in Fortnite, but that didn't really work for football, as I previously mentioned. So we started off by doing sort of prototypes based on fighting games like Mortal Kombat, and we did that sort of in Q3 2023. Back then it was Merkan and Marek, 2 guys there. It was great to do that. And then back in Q4, we hired a guy from Unity, the guy who was leading the DOTS network team at Unity. And we sort of embarked on rewriting this object-oriented code into data-oriented code. And by that time, we were running on 1.5 CPU cores on the game server. And that was for 2 players. Like, obviously, it's 11 versus 11, but you only are 2 players controlling it. So it takes a lot of performance there. So if you would be successful in scale, we would go bankrupt. So we needed to do something. And by like half a year later, we had the implementation done. We have ported most into data-oriented design, and you could say that the sort of SENTEC promise of making this faster was like an order of magnitude faster. So it was much faster in that sense. But we saw that, okay, we need to invest more. So we hired 2 more people like Adrian and Sophie, and we also brought in Timo from the core team, and we rewrote or we moved all the code from Unreal into its own standalone module. So it was sort of self-contained. We also moved away from floating point into using fixed point. And the importance here is like when you're using fixed point, you get even more deterministic results. Like floating point isn't deterministic, so you get even better like performance in terms of like stability in the network stream. But then came another sort of order of magnitude change, because once we had sort of finished the standalone work, we could actually move the entire game servers to be just SENTEC. So we went from using sort of SENTEC module in an Unreal game server to only using SENTEC. And that meant that we needed to rewrite our own sort of network stack, and everything that sort of comes with Unreal we need to do ourselves. But it gave us a huge performance boost, like 0.01 CPU cores. That's like super great. Then we felt like, yeah, this is sort of state-of-the-art technology. We need to patent this. So we have that patented actually. And we, by that time also, we got it working on ARM64. So ARM64 is like more power efficient cores, and those are also used in the servers. And they're also a bit cheaper, so you can get them running. So you get both the benefits of being less power hungry and usually cheaper to sort of use. And we also made investments in making sure that we could run the SENTEC code multi-core, like in multi-threaded environments. And Unreal, for you guys that don't know it, is like Unreal from a gameplay perspective is very single-threaded. So previously we were just running in the gameplay thread, but now we could run the actual gameplay in a separate thread, and that boosted performance basically for us. And then we have sort of initiative for 26 to, right now we're using GCP and sort of Agonis Kubernetes for the sort of server orchestration. That's sort of a Google owned thing. But we're feeling like we can probably do better if we find sort of a good approach to doing this. So saving even more performance and being able to scale at a lower cost is what we're looking at. And just looking at some raw numbers here, like we went from just going from the Unreal, even if it was sort of data-oriented coding there, but just doing that to just being completely self-sustained. It's a 12x performance on the CPU side, so it uses so much less CPU power basically. RAM, we went from 480 megs to 24 megs, so 20x performance increase there as well. Binary size, this is obviously like this is cloud, so you use a container, and the container was Unreal with sort of everything that comes with Unreal. But since we made ourselves, we just made an executable with some files, and that was just 15 megs. So from 1.5 gigs to 15 megs in terms of like size, that's 100x improvement in size. And that also couples with startup time, since you need to mount this, you need to sort of get it running and everything like that. So it went from 12 seconds to 0.08 seconds, so 150x performance improvements there on just doing this ourselves instead of using Unreal. Nothing of this matters if you don't get anything from the community. So like we playtest a lot with the community. We have the community all over the world. And as they say, like they're playing in the US against Europe, and that's like for our type of games, that's unheard of. Like nobody can do this. But we've been able to do this due to sort of the optimizations efforts that we've been doing. And it's great also for the competitive crew that's in sort of are competing in EFC, because there they can only compete between sort of Europe West, Europe East, and they split those regions, so you can't get ever a worldwide competition going. And obviously, like if you want to be the best in the world, you don't know. You're best in your region, and then you need to sort of travel to the final. So this opens up more from competitive play as well, because you can actually play against everyone. And as they say, that's incredible. Now we come to the next slide. So we've tackled the 3.1. This is the 3.9 that downloads and installs, and this is the launcher technology. So the headless launcher, what does it do? It detects hardware, downloads, install, and launches the game. And this solves the problem for games with very wide support in terms of performance scalability. So if you have low end to support something like a dual core Celeron with like integrated GPU and at least hitting 30 FPS, that's sort of what you want to do. But you still want to support like the really high end and don't really compromise on the visuals that you have there. So the high-end experience, it doesn't compromise with lowest common denominator because you've sort of split the problems in two. And you can use much of the Unreal Bling and high-end extensions that you couldn't do if you just choose a single path of just having one executable and one build. And on the low-end version, we're running with forward shading, which is less bandwidth consuming, and for this integrated graphics cards, it's around 30% faster. And we also can do sort of specific optimizations for low end, and it gives you faster load time, smaller download size because the content is less. You don't need to download the high end content if you're just using the low end one. And being able to play the game on less powerful hardware obviously increases the reach, and also the sort of Steam binary patching that we're using, since we're doing that sort of on the DLC basis, we can have the low end DLC, and if you're updating it, you're only updating the content that you actually need. So the patch size usually becomes quite small as well. And at a glance, how this sort of is set up. So the Headless launcher is a C# program that we make via sort of GitHub Actions. And then we have the Unreal Horde CI solution, which creates basically three versions. So we have like the common bundle, which is in the main game as well. So it's installed at the same time as the Headless launcher. And then we have the DLCs, which is the high-end DLC and the low-end DLC, which is also built there. And when you click play, we start up the Headless launcher. It does hardware detection. It either detects that this is a high-end computer, then it installs the high-end DLC together with the common depot, and then it launches the game basically. And on the high-end version, we also do sort of this Unreal benchmarking, so you get scalability levels like high, medium, low. On the low end part, it launches the game, but here it launches it based on sort of what hardware we have detected it, because we can't really run the Unreal hardware detection because it crashes the game. So here it actually sort of just uses predefined versions of it if you're running like on a really low end machine. And looking at sort of infrastructure, how this is built in more cases. So we made divergences in the Unreal build tool, so it knows about the low-end variant, and then we build and cook two variants at the same time. So we build the high-end version and the low-end version at the same time in the build system, and then we have a sort of a list of classes, and if the list of classes is 0, there's no like differentiation between low end and high end. We just put that in the common build, and then 1 to 4 is like either this is going to high end or low end, and that is typically sort of texture meshes and things like that, where we can do processing based on what is the target platform basically. And then we do a copy from the common bundle to the high end build. And we also obviously produce two executables. So we have the high-end executable and we have the low-end executable, and we put these in the DLCs. Excuse me. Right now, the size is around 2.9 to 3 gigs when they're combined. The high-end DLCs is around 433 megs. The low-end is 304. And we expect, obviously, this to grow the more content we have. Right now, we have like 2 levels. And Delta, as I said, is based on Steam binary patching. Biggest patch so far has been 800 megs, and that was when we sort of changed the level completely and sort of took out one and added one. But the regular patch is around 200 megs or smaller. And doing this sort of chunk-based approach also makes the delta smaller, because Unreal is not really deterministic in its way to sort of output chunk data. So it can, between runs, it can use the same thing and just change the order of files, which it shouldn't, but it does that. So if you chunk it up into smaller parts, it gets less changes, and then you get smaller patches as well. Headless launcher then. So it does hardware detection based on GPU, CPU, memory, GPU, and CPU feature level. It calculates scores to determine if the hardware should run on the performance or the experience version. It initiates downloads of the correct DLC, and then it launches the game. And the experience version, it is running D3D12 and shade mode 6.0, but it has also sort of like D3D12 is a very feature-rich API, and if you have a D3D12 compatible card, it might not mean that you actually have all of these sort of resource binding or feature levels. So if you don't have any of these sort of features, then you're also forced into the performance version, because if you're trying to use that, your game will basically crash. So we're checking for those when we do the detection as well. We also have a lot of like IHV plugins like XCSS, FSR, and DLSS. And those are like good for the high end because they sort of save performance. And if you have a high end sort of screen and visuals, it's going to make your game better and more performant. On the low end or performance version, it doesn't make sense because most of those hardware doesn't even support this type of thing. So including this in the executable wouldn't make sense because it takes up quite a lot of memory in the actual executable for this code to run. And there's a lot of like content as well that needs to be there. So just stripping all of these type of plugins that shouldn't be in the performance version also saves quite a lot of data. Then the performance low end version, it's running D3, D12 as well, but it's running with the shaded model 5.1 and a lot of less sort of feature levels that we have. We also have a D3D11 or DirectX 3D11 version, which runs shader model 5.0. And then we recently introduced an ES 3.1 mode, which is like mobile rendering, but we made it work on desktop basically. And that's actually great stuff. It gives a great performance. And then like on the CPU side, we have a reduced feature set. So for the CPU, so we don't have any AVX support in the performance build. And that means like computer that doesn't have AVX instructions can still run this build, and we detect that and we send all those players to the low end version. This is basically how we control the settings on the low end, since we don't really have any great like low, medium, high settings. So we just made half variant platform. So if you're using console, for instance, you usually have Xbox and things like that. So we use different or similar methodology here for the super low end and the low end, where we basically just define things. And we do that by these define device profile defines. But even if you're profiling a lot, you still play test with the community, and the community has surprisingly low-end hardware, even though you think like, who would ever have a graphic cards that came out in 2013? Well, people still have them. And then you have your QA guy saying like, do we have this? And no. And then you're looking at sort of, is this worth the investment? Should we actually go down the rabbit hole and actually trying to fix this? Because obviously this will take time and we will need to buy a lot of hardware. But like, since we have a lot of telemetry, like at least over 9% of our population right now is low end or targeted in the low end. It is a free to play game, and my experience, like coming from sort of mobile and free to play there, like when we did soft launches, we usually had sort of the enthusiast crew, and they are typically more high end, and then you launch the game and you get the plethora of like really low end devices. So my estimate would be, yeah, we're probably going to be close to 30% of low end devices when we launch this. And if you do optimization on these type of things to get the low end working, it usually trickles upwards, so it makes the gameplay performance better on mid spec and also high end. So it's a good thing to do. And digging deeper into this type of telemetry, like, is it worth looking at sort of the 4600 and that architecture series? And it showcased that sort of an Ivy Bridge Haswell generation of cards, and those are up to 25% still in the data we have. So it's still a significant amount. So of the 10%, it would be sort of equivalent to 2.5%. Which is like, it's still like, if you scale it up and have more players, it's still quite a lot of players that are playing on these things. So we decided to buy more hardware basically. So we did like Oprah Winfrey, you get a laptop, you get a laptop, you get a laptop, and we just handed out to the port developers, Mario, David, Sophie, and the other Torbjörn Leder, he got the short straw, so he got the Lenovo G500, which is the Intel HT 4000 graphics, which is kind of slow, to say the least. And when we worked on it, we got the game working, and we sort of, the community says like, yes, this is great. But there are obviously glitches and stuff like that that doesn't work, and it's kind of slow still. So we invested even more, and this is sort of the ES 3.1 rendering path, which is emulated forward shading. It runs 4 to 6 milliseconds faster compared to just pure D3D11. And with this, we actually been able to push this sort of potato device over 30 FPS. And we had a visit from Epic when you had the Unreal Fest here in Stockholm, and they sort of came over, they looked at the game, they gave us a tip and sort of showed us an article. And the article is sort of the QR code to the right. To the left, you have a QR code on a more recent discovery journey from another developer that went really deep on sort of the ES3 and how fast can you make actually Unreal run. And I think they are close to like over 800 FPS with not using all of the sort of settings they have. So you can do a lot of stuff if you're not like using everything which is done for cinematics. And this is basically how it runs. So like we're running at plus 30 and on this frame as if it was 46 FPS and it's running an HD ready resolution on this laptop. So it's native and it's playable. It's fast. Basically you can compete doing this. So, and our goal is obviously to push this a bit higher so you get more stable frame rate, because right now we have like a slight issue with frame pacing. So every other frame is not as fast, and that obviously give you a poorer experience. And this is also like going back to sort of the AVX thing, which is like instructions, and not to point fingers as anyone, but like if you remove this, obviously people will also be unhappy with you from sort of a consumer point of view, like because if you only have one executable and the game is crashing, the only reason you can do is remove this type of instruction set. But if you have two versions, then you don't need to remove it. You just target the people who have it to a different build. And the other approach is like if you have a patch and people are supposed to know about this, like I don't know anybody that actually knows what AVX is and you're a gamer. It's very, very few that are this type of hardcore experts that knows this. Like, so with the auto detection and just downloading the correct version of the game, you sort of get that problem out of the way and you have a much easier experience for the players. And obviously future work going to mobile is what we're looking into doing as well. We've built sort of the infrastructure, the architecture to do that, I would say. And we already have the game actually running on Android, but obviously we need to do more work on it. And it's running like over 60 FPS already on Android devices. And now we come into the last straw here. So the 311, the biggest one, and this is more about like throttling and how you can control the temperature of your gaming device. And why you should care here, like you have the player experience, like you look at this guy is sitting there, he's playing the game and it's turning to become quite hot. And if you don't throttle the game, you're going to get like a hot and very noisy game. And in some cases, it actually reboots the hardware. Like on the big desktop machines we had cases where it basically ran too hot and then it sort of rebooted the OS, which isn't great. And coupled to that, you have the cost of power, and this is not going to decrease. I think we have AI infrastructure coming up, a lot of other things. So I think the cost of power is just going to go up more and more. And then you have the CO2 output, obviously, like directly linked to power. And the cases is like, as I said previously, like high-end desktop uses more power than all of the others ones. So they uses between 200 to 500 watts on average. And I visited a sort of conference last week or 2 weeks ago where we talked about like high-end graphics, and it is coming hardware that has 1 kilowatt GPUs. So it's not going to decrease this type of like power intense usage basically. Laptops obviously uses less, but it's still 30 to 70 watts, and the phones are like slim in comparisons. That's 3 to 6 watts. So even if the population is much, much higher, the sort of desktops take so much more power versus them. And if we're looking at sort of ways I've seen that you can sort of reduce heat and get the better thermal processing, it is shader complexity is one thing that you can look at, getting that down. You also have bandwidth that you can look at and sort of reducing that. And bandwidth is typically something you look at more on mobile handhelds. You're not really concerned with that on desktop, but it gives you quite a lot of power save doing that. And then you have the big one for me at least, which is sort of how can we reduce the FPS to sort of cap basically the FPS in sort of so the GPU gets to rest and that's mainly during gameplay, but also the duration of the session. But reducing shader complexity is like what you can do there is like implement scalability settings in the shader, so we have good ones. Make it easy so the people that are interested in this actually can go in and change these things, because they will let the user control how much noise or fan stuff they also get. So if you reduce this, you'll get a better experience as well. And have good benchmarks, like when you're doing like hardware detection, make sure that those are tweaked so they are good in terms for your games, because what comes especially with Unreal is usually tweaked for sort of cinematic experience. It's not really tweaked for the game you are making. So you need to sort of look at the benchmarks, make sure that the features you're using, test that on the target hardware you think it's going to be working on. And then you can introduce something like echo or green mode, or perhaps just call it power saver mode. I would say that's probably a better word. And use that, and then you perhaps look at power efficiency and not FPS that you're looking at. Like, what is the actual most power efficient mode to visualize this game? And then you have like reducing bandwidth. Like if you reach your FPS target, usually then you stop. You don't care anymore. But then you can actually start looking at bandwidth optimization. Mobile does this quite a lot because you need to conserve battery time. But if you look at sort of fan noise and heat, you still can reduce this and get a better playing experience on desktop and laptops as well. So I would say it's a good thing to do investigations on this. And like there are a lot of different bandwidth optimization techniques. It's like, how can you interleave the data that you send over to the GPU, so you don't just send blocks of data and haven't really looked and sort of deeper level on the architecture, how they actually can use this. So it's there are a lot of algorithms which you can use here, and like looking at how the hardware actually works is a good thing. Then it's the big one for me at least, and this is sort of the things I've picked up. So there are 3 phases basically when you're playing the game where you can save performance, and obviously the big one is menus. You can just throttle these to 60, and what we've done, sort of you have 60 on the high end version and 30 on the low end version. And then if you go idle, there's no point in keeping that at 60, so you can just lower that even more. I know the guys in Fortnite have even sort of a mode where after 5 minutes, they sort of just go down to just a screen which you click. So yeah, you can do a lot here, especially like if you're gaming a lot and just going and eating dinner and just leaving the game on, there's no point in sort of rendering that game in 60 FPS. And from gameplay point of view, I would say this is probably the hardest one. Like, what can you actually do when you're in active gameplay, because you don't really want to sort of disrupt the gameplay experience. And VSync has often been sort of the answer I've been getting. Like, what can we do to solve this? Yeah, just put on VSync, but it doesn't really cap performance on new monitors. Like if you have 244 hertz monitors, like a lot of games doesn't even go there. Like our games is a bit faster, but it's still like it still doesn't get the problem solved. And you have new monitors with 1000 hertz frequency coming out next year, so it's not a silver bullet anymore. And like doing sort of an in-game fixed frame rate menu option is also what typically games have done for quite some time. And some gamers are also using sort of external programs like Riva Tuner or something similar to that. But no one has actually done anything from my knowledge around sort of throttling based on temperature like the mobile operating system does, or sort of handhelds. It's only kept on the OS level in those cases, but on desktop, I don't think it even exists. But what have we done then? So like the esport players, they obviously want high FPS, but no one really wants loud fan noise and a computer that almost burns up. And as we said, like quality settings and clamping FPS is how you reduce it. So we made a survey with the guys in our community and just asked them, like, we hear that you have problems with like heat, fan noise, and like the experience for your game isn't great. So we sampled some data and some comments from the community on Discord and just got some data. And for instance, this guy who has 153 and then he turns VSync on and he gets 60. And then he says like, yeah, but I don't want to play in 60. I'm a competitive guy. I want to be like at least 120, 130, but I don't want fan noise either. And some others are like saying, yeah, I'm running at sort of VSync on off, it doesn't really matter. Like it's 88 degrees when I'm having VSync off, and it's like 86 when it's on. So it doesn't give you that sort of fan distribution that you want to have. And some others are like yeah, fan noise isn't too bad, but the coil whine from the GPU is really annoying. So, and this is due to you're not throttling anything, you're just running without, and the VSync doesn't help in these cases. And some others are sort of scared about like the temperature on the CPU and GPU as well, that you're wondering if they need a new cooler or buy new hardware to actually fix these issues. So there's a lot of sort of sentiment from the community that this is a problem that needs to be taken care of. And what have we done then? So like we've done menu throttling. So we have like 60 FPS in the high-end version and 30 FPS in the performance version. And we also implemented recently like idle throttling. So after like 45 seconds, it just goes down to 15 FPS. And then if you touch the mouse, obviously it goes back to 60. But at least this is a sort of first step. I think later down the line, we'll probably do something similar to Epic, where they sort of go down even further after 5 minutes and just, hey, have a button that you click when you get back or something else, and just showcase like you're paused or something like that. But the real hard problem for us has been actually solving the gameplay thermal issues, like when you're actually playing in the game. And what we've built here, or what I built here, is like what we call GPU throttle. And it reads GPU data using sort of third party or like the GPU vendors APIs. And I've implemented 3 thermal modes. Like the fixed frame rate is basically what's common in the industry. But I've also did some experimental features, one called silent mode, which basically uses temperature and fan RPM, and then it's built like a regulator system. So it uses those as input variables, and then you adjust it with the FPS. So you're trying to reach those numbers that you've set in the menu, like you have temperature there. And the same goes for temperature. If you're sort of setting a target temperature, like here is 69 degrees, and you're trying to reach that by sort of lowering the FPS until you get a proper one. So it gives you a bit more unstable frame rate. So optimizing and getting frame pacing right is obviously a key for us, because then this won't be as bad either as well. So the frame pacing will be better. And how this is done then? So we've done Gold's GPU throttle. It reads GPU temperature, it reads GPU power usage, it reads the fan speed, and it implements NVML, ADLX, and IGCL. And then you have the Gold's GPU throttling subsystem, which handles the in-game state changes between sort of in-game, menu, and menu idle. And then you have the mode changes, which is fixed frame rate, silent, and temperature. And the implementation of this is like the NVIDIA model is using NVML, and it's basically a C-based API that is used mainly sort of in data centers. I think Tesla is also using this when they had NVIDIA graphics cards. So it's a pretty standard, easy to use. This didn't take that much time to actually implement. And as you can see, sort of the syntax is kind of easy. You just get device temperature and get power usage. Doesn't take that long to actually implement this. ADLX, the AMD counterpart, it's a bit trickier because AMD has sort of 2 ways to measure temperature. They have what they call hotspot and GPU temperature, and not all hardware supports the hotspot, so you need to do sort of detection for that. But still, it's not a lot of code, as you can see. It's sort of a C++ API instead of a C API, so you have to be more careful with how you do with the sort of memory allocations. It's using smart pointers and stuff like that. And the get power usage is straightforward, similar to basically how the NVML stuff worked. And then you have the Intel one. From a sort of perspective of their API, it basically does the same thing. It is a bit more cumbersome, sort of the Intel syntax. It looks more like driver like code, like very C-like. And a lot of things. So I had to think a bit more when I implemented this. But I had good help from the Intel team as well to help me find this for the first thing, and also actually helping me with the implementation of getting this right. This took a bit more time. And you also have, like, I didn't mention that, but the QR codes on the side here for the sort of recordings is where you can actually find the sample code for this. And looking at data then, like what does this actually do then? So since it's a regulator system and this is with the temperature throttling enabled, you can see that you get slight oscillations over time in the FPS, but then it sort of stabilizes itself. And the temperature kind of gets into a more stable feeling as well. And for this one, I was running at sort of, I think I had throttle around 70 and it tries to reach 70, but it's still a decent FPS, like 156 is decent and it doesn't jump that much in the end. So it was good reaching that. And the decibel level was at 41 decibel, so it's okay. But if you disable that, you can look at the temperature here as well. And you can see that it's increasing all the time. I think the dip you have is where we have halftime and the sort of throttling goes to 60 and then it goes back up. So you have a dip there. But even with the dip, you can see that the temperature is actually increasing over time, like for the time it's going. So you can imagine playing for a long duration of time, the temperature is not going to go down if you don't throttle quite a lot. And the FPS is, as you can see, it's a bit flickery, but it's not as much as sort of on the regulator system. And the FPS is obviously much higher. It's like 270, so it's almost 100 FPS faster. But it's also running at 88 degrees, and I can tell you, as you can see on the decibel counter, the fan started to be really loud noise here. And then you look at power usage, and the power curves are basically as it showcases sort of a regulator system curve. It starts off by sort of being high, and then it goes down into sort of where the temperature is at. And then you have halftime, and then it goes back up again, and it sort of regulates down. And then if you look at with throttling disable, it just maxes out and just continues to be maxed out all the way. And doing sort of a projection of energy consumption, not going for the Fortnite scale, but like what could be if we are successful, we would hopefully get something close to Rocket League at least. But the yearly cost saving, if we would assume that people were using this thermal throttling, and we also have this sort of menu throttling in there, I would say the sort of yearly energy savings would be like 5.3 million kilowatt hours, which is still quite a lot. Like the yearly cost savings would be close to $800,000, and the CO2 saving would be 2.5 million kilograms of CO2. And that's just doing sort of this type of throttling. It's not super advanced, and that would be sort of 2098 flights from New York to Los Angeles. So if you can think, if you're interested in these things and you feel like, okay, this might be something I could do for the game, I think it could be worth investment for sort of trying to take more impact. But we also have telemetry on this. So in order not to just do assumptions, but actually sort of look at real world data. So with this, we just showcase that we can measure it. It's a system that works at scale. Not all GPUs support this, obviously. So you get the data and you can see the problem is that gamers don't know about it. They have no idea what this is. It's not really in your face. They have no clue what it is. And when they know, you can see that fixed frame rate is the clear number one. And we can see that sort of silent is a bit lower and temperature is a bit higher, but it's not huge amount of people that are looking into these things. And it's the sort of curious people that are going into the video settings and actually looking on these things. But it tells you a picture that you need to sort of give stuff more in your face, I would say. But this I did in the prior to this presentation, and this is actually showcasing real-time CO2 calculations. So we have the energy, we can calculate how much energy we have, and what I've done is actually getting out the CO2 of where you live and be able to calculate how much CO2 you're actually using for you. So you can actually make sort of an effect on your own CO2 consumption. And when I did sort of a short research on this, like there are a couple of APIs that gives you this type of data. So you have electricity maps, you have carbon intensity API and some other APIs. And I ended up using electricity maps. It gave me sort of a good carbon intensity overview over the entire world, basically, even if it might not be sort of super accurate in all cases, it's accurate enough, I would say. It's better than getting sort of an average. And the way I've implemented is like we have the GPU power from the third-party APIs. We convert watts to kilowatts using delta time, accumulate that to session energy kilowatt hours. Then we have geolocation. So I implemented sort of a simple geolocation API as well that just gives you longitude and latitude. And I feed that into the electricity API, and it gives you the correct carbon intensity for that where you actually live. And obviously, like for some countries where you can choose to have a different distribution, this might not be accurate, but I would say it's still accurate enough for the sort of power consumption within that country. And this value is also cached for an entire session, so you're not like doing this over and over again. And each tick, this computes sort of the CO2 in grams, and it uses the energy since last tick and the carbon intensity, and then it adds this to the session CO2 in grams, which is the total as you see there. And we use this to have this logged in the GPU throttle telemetry. Future work on this, like obviously we need to improve the UI on this, add more on-screen counters, as we've talked about, like getting this in your face, being able to see these things, so it's good. Implement some form of like echo or power efficiency mode would obviously be good from the quality levels perspective. Also, we have like an WinARM 64 native Windows 11 build as well. The problem is though that there is no store that actually supports this. Like Steam doesn't support this, Microsoft Store doesn't support this. I'm not sure that Epic support it might do, but we don't have any sort of implementation for Epic Store. So there is a big need to get sort of a WinARM system, because like these type of machines, this is made from Qualcomm, and they have much more power efficiency built in because ARM is a better architecture in terms of power efficiency compared to like x86 because it comes from mobile. And then obviously like collaborate more with SGA as we talked about. So yeah, that's everything. A bit over time, but hopefully it's okay. Q&A.
Yes, I think most of us, I absolutely floored by the amount of detail in there, and a huge amount of work to digest. And yeah, I absolutely am super glad that you did go over time, because I wanted to make sure that we gave it the appropriate space to devote to it. So wonderful. We are almost out of time now, though. I have like so many notes, and I have a bunch of questions that I could ask, but I wanted to throw it open to the audience first. Does anyone have a question for Torbjörn that you'd like to ask in particular? What would you recommend for someone who maybe doesn't have your level of, I guess, hardware expertise? Where would you start out of these options? Like, what should we
Like the
begin
easiest
with?
by far is like menu throttling. Like that's super simple. You just detect, am I in the menu? Yes.
Mm-hmm.
Throttle to 60. Am I not in the menu? Leave it unbound. That's what I started with as well, because that's basically as ordinary logic when you go between sort of states. So that's kind of simple.
Mm.
Idle detection is not super hard either. There might be some cases there, but what you actually can do is like use the sort of AI tools that are now, like you can use ChatGPT to sort of bounce ideas with, like how should I implement this, and then test, and then obviously you need to refine the code, because what those APIs give you might, or those like AI tools give you, might not be the sort of best implementation. So, but it's good for rubber ducking, basically coming up with ideas and then sort of implementing those ideas as well. And that's how I implemented the CO2 stuff in, I think, a day. I did that,
Mm.
and that's just by sort of rubber ducking with ChatGPT and just asking how could we do this? What is the sort of options for doing that? And then implementing it, obviously cleaning up the code which it produces. But it is a good tool to use AI for these things, because if you have no understanding of underlying hardware, at least you'll get some direction for it. The key point is you need to understand what questions to ask. I think that's the answer.
Mm. Mm. Would I mean, yeah, so one of the most striking things I think in the presentation there was the graph you had of the temperature chart of like a GPU over time in
Mm,
unthrottled mode, and it just kind of going up and up and up and up.
yeah.
what that made me think of, and I'm curious to get your perspective on, is like whether you think there's an assumption maybe in the default approach that game developers take to the hardware that they will just sort of operate, that they won't break themselves,
Mm, mm,
they won't overheat and
yeah,
melt. Do
yeah.
you think that that's like do you think that that's out there in the industry?
I think they don't really think about this, to be honest. Like when I was at sort of the graphic programming conference, I did a similar presentation on this, and a lot of the people there are really hardcore GPU programmers. They are great at what they're doing. But seeing this, they sort of, yeah, I haven't thought about this. So
Mm,
I think there is a shift and there's need to be sort of an education and sort of we need to surface this because like in the end of the day, this isn't hard. Like the things they are doing, that's hard. Like that requires like really great programmers to do.
mm,
This is something I've done sort of as a side project, a side quest, basically.
mm,
I'm a technical director, so I mainly sit in meetings, but I had the time to do this sort of between meetings and sort of doing stuff. And I still got pretty good results, and I haven't seen that many actually doing something different or
mm,
more than what I do. Obviously, the Fortnite guys have done more in terms of sort of the idle throttling that I've been doing, but it's not it's definitely not rocket science, I would say. This is easy
mm,
peasy things. But what we also talked about is like there should be initiative from sort of Kronos, which is sort of this uh, it's a board for dealing with APIs and large scale APIs for hardware vendors. And they talked about like why shouldn't we have like a direct power or something like that? Because obviously for game developers, even though this what I showcased in sort of getting power from MVML, ADLX, and IGCL, it's not hard, but it's still cumbersome to implement. Like
mm,
it takes some time to do this right. Getting a sort of a standardized API for all hardware vendors to implement, I think that would be great because like why shouldn't you be able to read the GPU power? Why shouldn't you be able to read the temperature? Why shouldn't you be able to read the fan speed? As long as you
mm.
can't like set it, because I understand from a driver guy's perspective, like if you start to fiddling with the sort of, oh, I'm going to reduce the fan speed. Yeah, that's probably not
Yeah,
a good idea. But
bit
if you,
risky.
yeah, it's a bit risky. But if you can do that via sort of lowering the FPS, so you use it as I did, like for regulator system and stuff like that, then I think it's
Mm,
safe because then you're not actually sort of accessing data in the driver. So yeah.
mm. There's just one quick question that has appeared in the chat before we wrap up. Do you have any tips for QA? How could we assist in the optimization process? Great question.
Yeah, but I think sort of without having any types of tools right now, but there are sort of you can measure power efficiency based on the entire system at least. So doing that is like at least the first step. But I would argue that getting developers to at least try to implement some of these so you can actually read the power consumption makes it so much easier because then QA could basically because you can print this out in logs and stuff like that and then QA could look that over and see like are we using too much power if you're trying to have like most games has like an FPS target, but what should be our sort of power efficiency target on a
Mm,
certain like hardware spec, for instance, like, and that could be achieved from doing this. I would say so.
mm.
That could be a thing.
All right. Well, I think we're out of time, so we better let you and our audience go. But please, again, thank you. Please join me in thanking Torbjörn for such a mind-blowing presentation and super super fascinating work that I hope we can start to move forward with and disseminate across the industry. So
Mm.
thanks everyone for coming, and
Thank you.
yeah.